All right, so we have the integral of e to the 2x over e to the 2x plus 3e to the x plus 2. Doesn't look like there's anything super obvious, so we kind of just start guessing. I'm going to make the correct guess here that we should do a u sub first. We should let u equal e to the x for a couple reasons. One, and really the main reason is that its derivative is also there. The derivative of e to the x is e to the x. And so we can break apart this numerator as e to the x times e to the x. You might be asking, well, James, why didn't you pick e to the 2x? Fair question. You pick u equal to e to the 2x, your derivative would be 2e to the 2x. And you also have that up top. But that's going to make substituting it for the denominator harder. If I let u equal e to the x, that e to the x is going to be a u, and that e to the 2x is going to be a u squared. So that's what's kind of driving my choice here. So I'm going to rewrite this a little bit. I'm going to write it as the integral of e to the x times e to the x over e to the x squared plus 3e to the x plus 2. So that now we can say, oh, look, there's our du, which is equal to e to the x times dx. And every other e to the x gets to be a u. So there's a u, there's a u, there's a u. And we can rewrite this as the integral of u over u squared plus 3u plus 2 du. And now it's a partial fractions problem. Because now we have a rational function where the degree on top is less than the degree on the bottom, and the denominator factors as u plus 2 times u plus 1. So we're going to know that this is the integral of u over u plus 1 times u plus 2. And then we're going to do a partial fraction decomposition. So we're going to say that u over u plus 1 times u plus 2 is equal to a over u plus 1 plus b over u plus 2. This is kind of the best partial fraction decomposition situation because everything is a linear factor raised to the first power, right? You don't have any repeated powers here, so it's going to be pretty nice and easy. We're going to multiply both sides by the common denominator. We're going to get u on the left. We're going to get a times u plus 2 on the right, plus b times u plus 1. I didn't actually write out the step of multiplying by the common denominator, but I think we can all handle multiplying both sides by u plus 1 times u plus 2. Then we start picking convenient values of u. I'm going to pick u equal to negative 2. When I do that, I get negative 2 on the left, I get a times 0, and I get b times negative 1, which means b is going to equal positive 2. Similarly, we're going to pick u equal to negative 1. We're going to get negative 1 on the left. We're going to get a times positive 1 plus b times 0. So we're going to get a equal to negative 1. Oh, thank you. Yes. So then we're going to rewrite our integral of u over u plus 1 times u plus 2 as the integral of a over u plus 1 plus b over u plus 2. We integrate. We get negative 1 times the natural log of the absolute value of u plus 1 plus 2 times the natural log of the absolute value of u plus 2 plus c. And then since our integral started off with x's and it's indefinite, it better end with x's. So we have to substitute back in what we said u was equal to in the first place. So that's going to be the negative natural log of the absolute value of e to the x plus 1 plus 2 times the natural log of the absolute value of e to the x plus 2 plus c. I will point out it would be equally correct to write this answer without the absolute value, just since e to the x plus 1 and e to the x plus 2 are both always positive. So in the textbook answers section, you might see this written as negative natural log of parentheses e to the x plus 1 plus 2 natural log of parentheses e to the x plus 2 plus c. Fun. Questions about any of that madness? Like, yes, all the questions we're going to ask them. Okay. It's not too bad, but definitely the first step of seeing the u substitution takes a little bit of practice. Yeah, let's look at that one. That's clearly, I think is clearly maybe a partial fraction. I think it's a partial fraction. Maybe not. Let's look at the one on the board that's ax over x squared minus bx. I'm curious about that. The integral of a times x over x squared minus b times x. I feel like this problem isn't as terrible as it looks. Ooh, and after this, I have something I remember to say. To me, it looks like we could factor out an x from the bottom and say it's a times x over x times x minus b. Then the x's get to cancel, and you have the integral of a over x minus b. Or if you prefer, a times the integral of 1 over x minus b, which is then equal to a times the natural log of the absolute value of x minus b plus the constant. Don't think there's anything else going on there. Yeah. Yeah. Are there more questions about this problem? Or I mean, I feel like I'm missing something because it feels, I don't know, more straightforward than I imagined when I looked at it. Questions, comments, concerns? You could also have done this using partial fractions, but again, I would always say that partial fractions is a method of later resort. If there's an easier way to do it, you should do it the easier way. That said, let me do something real quick here. Sorry, one sec. Let's see, that's going to be x squared plus x squared plus 1. Cool. Let me ask about something like this. The integral of 2x squared plus x plus 1 over x cubed plus x. Okay, so before we get too into this, I'm going to say two things. One, this does meet the criteria for partial fractions. Rational function, degree on top is less than the degree on the bottom, and the bottom factors. But here's what I want to point out, because I'm not sure if you guys have talked about this in your classes or if you're expected to do this or not. So here's, I want to show that if we factor the bottom, it's going to factor as x times x squared plus 1. And x squared plus 1 is an irreducible quadratic factor. It does not factor any further. So here's my question to you all. Has your class talked about irreducible quadratic factors? Are you expected to be able to anti-differentiate that? Anyone yes? Anyone yes? Anyone yes? Great, then we won't do it. I'll point out that it involves the arctangent, but it's kind of a pain in the butt. So if that's not something you all are doing, we will never do this or save it for when it comes up. When/if it comes up. All right. Okay, that covers that. Oh yeah, let's talk about some. I really find it intriguing that this class talks about improper integrals before it talks about area between curves, but it does. It seems odd to me. So okay. Well, let's talk about improper integrals because that's clearly what we have on the board over there. Ooh, yeah. All right. So improper integrals. So what makes an integral improper? Well, there's actually two types, but I'm guessing you might only be seeing the first type. So the first type of improper integral has either infinity, negative infinity, or both as limits of integration. That is the defining feature of a type 1 improper integral. And just I'll say the words for type 2, if we need to see them, it's that the function you're integrating is undefined somewhere on the interval of integration. So that's a type 2. I don't know. Are you guys seeing type 2s as well? No? Okay, great. So we'll stick to type 1, which is great. So I imagine your teachers all probably showed you this example, the integral from 1 to infinity of 1 over x dx. Like that's a super common first example. The region that you're talking about looks like you're taking the function 1 over x and just starting at 1 and finding all the area underneath. What we're going to do is we're actually going to say, well, we're going to stop at b. So we're going to find that area first. So first we're going to look at the integral from 1 to b of 1 over x dx. I'm kind of doing this a little bit of a more roundabout way than I usually would, but trust me, it's going to be fine. You can use B or any letter you like. Typical to use B for an upper limit, A for a lower limit. Some people like to use T or Z, but A and B are pretty common for lower and upper. So we're going to write this at, well, we're going to evaluate it as, let's see, the antiderivative of 1 over x is the natural log of the absolute value of x from 1 to b. We're going to get the natural log of the absolute value of b minus the natural log of the absolute value of 1, but that's just going to be the natural log of 1, which is 0. So the area under this curve from x equals 1 to x equals b is the natural log of b. So if b was 10, the area would be the natural log of 10. If b was 1 billion, the area would be the natural log of 1 billion, whatever that number is. It's actually not that big. Someone should find out what the natural log of 1 billion is and tell me, because it's probably like, I don't know, 5 or 10 or something. Like, it's really not that large. But the point here is that we want to let b get infinitely large. And so if we want to find the actual, what the improper integral is doing, we write it as the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And then we do the integral. We get the limit still as b goes to infinity. I'm going to skip this step and go straight to here and say, it's that I already did the work. Its limit as b goes to infinity of the natural log of b. And this is a really good time to have an idea of what the natural log function looks like in your head. Because the easiest way to think about what this limit is by just thinking about what the graph is doing. Think about the graph of the natural log function. It's getting bigger and bigger and bigger and bigger as you go further to the right. It's not doing it very fast, but it keeps getting larger and larger. It does get large without bound. In other words, the limit is infinity. So what does that mean? It means the area under this curve is infinite. It means this improper integral is divergent. So this integral from 1 to infinity of 1 over x dx diverges, or is divergent, however you want to say it. Saying it's equal to infinity implies all that. So if you just say it's equal to infinity, that's enough to say, yes, you also mean it diverges, unless WebWork is asking you to write the word diverges. Questions? Okay, keep going. So not every improper integral diverges. That would be boring. Some of them converge. Like, let's skip the next typical example and do this one, the integral from 1 to infinity of 1 over x cubed. Same idea. We've got this area under this curve. When I draw these curves, they look, unfortunately, too similar. 1 over x cubed gets smaller faster, though. It's like that. And we're looking at this area here. And we're asking, okay, how much area is there? Or really, what's the limit of the area? So when you're computing an improper integral, I should point out, an improper integral is a definite integral. Right? Definite integral just means you've got limits of integration, whether they're actual numbers or infinity. Still a definite integral. Whenever you have an improper one with an infinity or a negative infinity, the first step is to write it as the limit as b approaches infinity or a approaches negative infinity of the integral from 1 to b. And I would rewrite this as x to the negative third. Always your first step. Just replace your infinity with a letter. I like the letter b, and then write the limit as that letter approaches that value in that direction. Then we do the integral. The antiderivative. We use the second part of the fundamental theorem of calculus. We antidifferentiate this. We get x to the negative 2 over negative 2, evaluated from 1 to b. I don't love thinking about infinity to a negative power. So while your next step could be this, the limit as b goes to infinity of b to the negative 2 over negative 2 minus 1 to the negative 2 over negative 2, I would really rather rewrite that as the limit as b goes to infinity of 1 over negative 2 times b squared, minus a minus is plus, 1 to any power is 1, so you just have 1 over 2. That's how I would like to rewrite this. So then I can see that, oh, b is getting infinitely large. 1 divided by something that's infinitely large is going to get infinitesimally small. So that's going to be the 0. So this integral is equal to 1/2. So we could say the words, this integral converges to the value of 1/2. So the integral from 1 to infinity of 1 over x cubed dx converges to 1/2. but it's just as good to say it equals 1/2, and people know what you mean when you say that. Cool. That one, we're close. Let's see. Yeah, let's do that in a second. Let's look at the integral from e to infinity of x over the natural log of x cubed. And I could write that here, but I don't want to kind of squeeze it in, so I'll just do it over here. The integral from e to infinity of 1 over x times the natural log of x cubed. Okay, so I'm still going to start off the usual first step by writing it as the limit as b approaches infinity of the integral from e to b of 1 over x times natural log of x cubed dx. So here's something that I usually do if I know my method of antidifferentiation is going to be more complicated than just like knowing what the antiderivative was. Like for those previous two problems, we knew the antiderivative of 1 over x with the natural log of x. We knew that the antiderivative of x to the negative third was x to the negative 2 over negative 2, right? We didn't have to use any methods of integration. Not so here. Right? Here I'm going to have to do, I think, a u sub. So since I don't want to write all that along with the limit and the limits of integration every single step. So what I usually do is off to the side here, I do the antiderivative of the indefinite interval. I'm sorry. So I'm going to let u equal natural log of x. And my du is going to be the derivative, which is 1 over x dx. And that's going to work out perfectly. This is going to be the integral of 1 over, I should deal with it. So the dx over x is my du, and then I have a 1 over u cubed. We just integrated x to the negative third and got x to the negative 2 over negative 2. It's the same deal here. This is going to be u to the negative 2 over negative 2, which I would always is strong, almost always rather write as negative 1 over 2u squared. And then let's plug back in that u is equal to the natural log of x. So we get negative 1 over 2 times the natural log of x squared. So now I know what the antiderivative of this function is. And so then over here in my next step, I can write this as the limit as b approaches infinity of the antiderivative, negative 1 over 2 times the natural log of x squared, evaluated from e to b. To me, that just seems much better than doing all this work while carrying along the limit and the limits of integration. So that's what I would recommend whenever your improper integral looks like it's going to require u substitution or integration by parts or partial fractions or anything else that sucks like that. So then we plug in the limit is b goes to infinity of negative 1 over 2 times the natural log of b squared minus a minus is plus 1 over 2 times the natural log of e squared. Okay. So typically when I'm doing this, I'm either thinking that my numerator is really big or my denominator is really big. If the numerator is big, it's going to diverge to infinity. If the denominator is big, it's going to converge, or that piece is going to converge to 0. So this looks like it's converging to 0 plus whatever this is, which is 1/2, because the natural log of e is equal to 1. This is going to be just 0 plus 1/2, which is 1/2. Ooh. All right, there's something I'm trying to wrap my mind around here for a second. Sure. Yeah, that's fine. Oh yeah, we should do something like that. Okay, cool. Questions before we do another one? All right. You're always welcome to ask questions. I should stop asking if you have questions. If you have questions, you're going to ask them, or you should. I'm really always happy to pause for questions and explain something from greater length. Yeah, there's just something that my mind is circling around here that I know I'm thinking about, but it's not quite gelling. Oh well, it'll come to me. Let's look at the following: the integral from negative infinity to 0 of x squared e to the x dx. Yeah. Yeah, yes is right. Before we do anything, in fact, I want you all to write down the first step. What's your first step going to be here? Write it down. Equals something. Only do the first step. You don't have to do any more than just the first step. Oh, that I remember what it was. Okay, yeah, cool. Remember that. Yeah. Improper. Um, all right. So this should be your first step. The limit as a approaches negative infinity of the interval from a to 0 of x squared e to the x dx. That's it. That's every time if it's improper, it should always be the first step is just to write it with the limit. And then we have to integrate x squared e to the x, and it's going to be integration by parts twice. Fortunately, this is one of those integration by parts problems that we could use tabular integration for. That's what we're going to do. So our u would be x squared or e to the x? X squared. Be careful. I've helped a few people with some integration by parts problems, and I've seen that they've been picking u equal to x to the third, even when there was like a natural log of x to pick. If there's a natural log of x, you're doing integration by parts, that should be your choice for u, not whatever x to the power is. And then our dv is going to be the rest. E to the x, I'm not going to write the dx because we typically don't. We're doing it tabular style. All the derivatives of x squared until we get to 0. So 2x and then 2 and then 0. All the antiderivatives of e to the x, which is just e to the x every time. And then we do positive x squared times e to the x minus 2x times e to the x plus 2 times e to the x. So this is going to equal the limit as a approaches negative infinity of this hot mess here, x squared e to the x minus 2x e to the x plus 2 e to the x, evaluated from a to 0. How do we want to do this, James? Yeah, sure. Just trying to think about how this is to make this not awful for you all. No, let's make it awful. So plug in. Limit as a goes to minus infinity. When you plug in 0, I'm going to get 0 times e to the x minus 0 times e to the x plus 2 times e to the x. So that's going to be, sorry, 2 times, whoa. Let me back that up. 0 times e to the 0 minus 0 times e to the 0 plus 2 times e to the 0. The first two are just 0, but the last one is 2 times 1, which is 2. Minus, now we plug in a, and we get a squared e to the a minus 2a e to the a plus 2 e to the a. Do not love this. I'm trying to avoid just telling you the easy way to do this, but I guess I should just tell you the easy way to do it. So here's what we've unfortunately got. We've got a squared and 2a, and which are both getting infinitely large or negatively infinitely large. And you've got e to the a, which is going to e to the negative infinity, which is going to 0. So what we really have here is an infinity times a 0. Or I should say a really big thing times a really small thing. And a really big thing times a really small thing can kind of be anything. It's actually one of these indeterminate forms. So the way you should rewrite this, and really the better way to do this, is to do the following. I should be smart and factor out an e to the a for everything. So write this as 2 minus e to the a times a squared minus 2a plus 2. And I'm actually going to bring this e to the a down to the denominator as e to the negative a. The reason I'm doing that is so that I can use L'Hopital's rule, which hopefully all of you got to see in 17a. Apologies if you didn't. But here's how it works. So why have I written it this way? Because now my numerator is going to infinity in some sort of way. Actually, it's going to positive infinity, right? Negative infinity squared minus 2 times negative infinity is an infinity plus an infinity, which is infinity. And my denominator is going to e to the negative infinity, which is e to the infinity, which is infinitely large. So what we have here is an infinity over infinity. And when you have an infinity over infinity limit, we can use L'Hopital's rule. You can also use L'Hopital's rule when you have a what over what? Yeah, a 0 over 0. So 0 over 0 or infinity over infinity, you can use L'Hopital's rule. What is L'Hopital's rule? L'Hopital's rule says that if you have one of those two types of limits, you can take the derivative of the top and the derivative of the bottom, take the limit of that, and the answer is the same. In other words, L'Hopital's rule says that the limit as x goes to whatever of f of x over g of x is equal to the limit as x goes to whatever of the derivative of f of x over the derivative of g of x, as long as it's a 0 over 0 or infinity over infinity type. So that's the very, very short of how L'Hopital's rule gets applied. So here, I'm just going to bring this 2 out in front because it can just kind of chill there. We're going to take the derivative of the top, which is 2a minus 2, over the derivative of the bottom, which is negative e to the negative a. And we still have an infinity over infinity type. Technically, it's negative infinity over negative infinity, but I don't really care about the signs. So then we do it again. And usually when I'm using L'Hopital's rule, I like to write a little L apostrophe H. So the person who's grading my work knows I used L'Hopital's rule. If we do it one more time, and I should write the 2 out in front still, 2 minus the limit as a approaches negative infinity. The derivative of the top is 2. The derivative of the bottom is positive e to the negative a. And now you have something that's going to 2 over infinity, which is getting smaller and smaller and smaller. That's going to go to 0. So we get 2 minus 0, which is 2. So this integral converges to 2. Here's the shorter, hand-wavier way to do it. If you have an expression, a rational wrong here, a quotient expression, and one piece is polynomial, and the other piece is exponential, the exponential is always going to win. Meaning e to the x always beats out x to any power. So I knew when I wrote this down that this e to the negative a was going to overpower this a squared minus 2a plus 2. And it could have really been a to the 1,000th minus, whatever. So exponentials always win. So this thing's getting bigger faster. So my denominator is the bigger thing. So the fraction is getting smaller. So exponential functions always overpower polynomial functions eventually. As long as the exponent is getting large, which is why I need the negative infinity. So the exponent is getting large. Ooh, kind of a pain. Interesting. All right. What time is it? Yeah, we got some time. Sure. Well, let's look at that other one on the board there. That's not a word problem yet. So it's extra special when both limits of integration are terrible. So in this case, when you have the integral from a negative infinity to infinity of x squared over 9 plus x to the 6th. Interesting here. So typically for a problem like this, you would have to break it up. So as I like to say, for improper integrals, you can only deal with one problem at a time. This improper integral has 2 problems, infinity and negative infinity. So we have to break it up somewhere. The usual choice is at 0, but any choice is actually valid. You can break it up at 1 or at 5 or at pi or at negative 17. Any choice is fine, but the usual choice is 0. So we're going to write this as the integral from negative infinity to 0 of x squared over 9 plus x to the 6th dx, plus the integral from 0 to infinity of x squared over 9 plus x to the 6th. And let's see, how do I want to say this the right way? That's interesting. Oh, that's going to be terrible. Okay. Sorry, I'm just trying to think about what I want to say here. So for this particular example, I would point out that x squared over 9 plus x to the 6th is an even function. Meaning if you graphed it, it has symmetry about the y-axis. You guys look like you don't believe me, so let me show you. I mean, I think you believe me, but let me actually show you, because I don't like just saying things. Be like, yeah, it does the thing, and you should all just believe me without thinking about it for yourself. You should definitely think about it for yourself. Well, let's just graph it real quick. So we have what? X squared over 9 plus x to the 6th. 9, yeah. And it's super shallow, but if you look at it, right, you can definitely see the even symmetry, right? It's doing the same thing on the right and the left. So what we could do to make our lives easier is say that this is equal to, sorry, you can't see what I'm writing. One moment. This is equal to 2 times the integral from 0 to infinity of x squared over 9 plus x to the 6th. All right, so let's do it that way. And we'll probably try to do one more like this where, yeah, we'll do something else. Okay, so any bright ideas? Let me ask you a question. So I see that I have x squared times dx on top. If I was trying to pick a u so that the derivative of u was also in there, what might be a good choice for u so that the derivative of u was close to x squared? X to the what? What x to what power? If I took the derivative, would be essentially x squared. I want my derivative to be x squared, maybe with a coefficient. What power do I need here so that my derivative is x to the second power? Right, I need x to the third. So if u is x to the third, my du is going to be 3x squared dx. So that, when there's not an obvious choice for you in the u sub, that's one way we try to look at it. It's like, well, what could I pick so the derivative still shows up? And that's actually the more important part. So that if you're looking for a thing to pick, that's how I would recommend looking at it first. What can I pick for u so that the derivative of u is in my interval? Great, let's make it work, as Tim Gunn says. So 1/3 du equals x squared dx. And then things are going to be, So again, I should point out a few things here. I've broken my own rules. I didn't write the limit first. Oh my God. Let's fix this. So this should be the limit as b approaches infinity of 2 times the interval from 0 to b of x squared over 9 plus x to the 60x. But then, since I'm having to use a method that's going to take up more writing space than I really want to, I'm going to do that off to the side for the indefinite. So I'm going to look at the interval of x squared over 9 plus x to the 6th here. And yes, my x squared dx is exactly my 1/3 du. So I have the integral of 1/3 du. And then my denominator, well, what does x to the 6th become in terms of u? Well, if u is x cubed, then u squared is x cubed squared, which is x to the 6th. This looks like a 9 plus u squared. Okay. Do we know how to integrate this? I saw someone mouth it. Say it loud. Come on. Starts with an A. Yes, arctangent. Ooh, but it's not just arctangent to u, because there's a 9 there. So here's what I would recommend memorizing, to be perfectly frank. Integral of 1 over some number squared plus x squared, instead of just 1 plus x squared, is 1 over that number times the arctangent of x over that number. Plus c. Sorry. So the integral of 1 over 9 plus u squared is going to be 1 over, so that 1/3 is just from right there. And then it's going to be 1/3 times the arctangent of x over 3. Sorry, u over 3. Gross. So that's going to end up being 1/9 times the arctangent of x cubed over 3. Good times. All right. And yeah, I mean, so there is a way you can do this. Like, if you wanted to show the work here, what you would have to do is factor out a 9 from the bottom and then do another u substitution, letting u equal like u over 3. It's a terrible pain in the ass. Do it this way. Memorize this formula. All right. So this ends up being the limit as b approaches infinity of 2 times my integral, which was 1/9 times arctangent of x cubed over 3. You know that typical function. Evaluated from 0 to b, we plug in, we get the limit as b goes to infinity of 2/9 times the arctangent of b cubed over 3 minus 2/9 times the arctangent of 0. Okay, first question. Arctangent of 0. What's the angle that if you took tangent of that angle, you would get 0? 0. Tangent of 0 is 0, so arctangent of 0 is 0. Side question. What's the arctangent of 1? What's the angle? If you took tangent of that angle, you would get a value of 1 in degrees or radians. Correct, pi over 4, or 45 degrees. Okay, so as b goes to infinity, we're taking the arctangent of a really, really big number. If you think about the tangent function, so really we're asking tangent of what angle is a really big number. Think about the tangent graph for a second. How it does this sort of deal, and then as the vertical asymptote gets really, really, really big, as the angle gets closer and closer to pi over 2. Right? There's a vertical asymptote for the tangent function at pi over 2. So as the values get infinitely large, the angles get closer to pi over 2. Or if you graph the inverse tangent function or the arctangent function, which looks like this, has a horizontal asymptote at pi over 2 and negative pi over 2, your arctangent function looks vaguely like this. And so as x, or as the input gets really large, the output gets closer and closer and closer to pi over 2. And that's kind of just something you have to know. There isn't really any other way to say it other than there's the graph. So we end up getting 2/9 times pi over 2 minus 0, which is pi over 9. Hopefully. Hopefully I didn't make an error anywhere. Exciting times. We might not get to that fish problem today, but we'll definitely get to it next time. I do want to say one more thing about improper integrals, and I'll try to address something like that. So this problem was kind of unique in that it was a nice even function. So we were able to split it up and basically break it in half, double it. But not everyone's going to work like that. So what if we had something more like the integral from negative infinity to infinity of x times e to the negative x dx? So this is one that we should break up as well. Again, anything where you have both limits of integration being infinities, you have to break it up. Still going to break it up at 0. So from negative infinity to 0 of x e to the negative x plus the integral from 0 to infinity of x e to the negative x. And then we actually have to do each integral. And here's what's going to happen. If both integrals converge, then the whole thing converges to whatever they add up to. So you'd find this one, you'd find this one. If they both equal the number, you'd add the numbers, that would be your result. If one of them diverges, the whole thing diverges. You shouldn't even look at the second one. With the caveat that if they ask you what it diverges to, then you do have to look at the second one. But hopefully they're not asking you that because it's annoying. What that means for us is that we should try to look at this and ask ourselves, well, which one do we think might diverge? Because if you can pick the one that diverges to do first, then you don't have to do the work of doing the other one. So if I look at this, I'm seeing that this one here, where negative infinity is one of the limits of integration, looks like it's going to be probably divergent, because here's what I'm thinking. If I plug in negative infinity for x, I'm getting negative infinity, a very large negative number, times e to the positive infinity, a very large positive number. And a big negative number times a big positive number is going to, the function itself is going to be really big, and then the area under that is probably going to be even bigger. So if I had to guess which piece was going to diverge, I think it's that first piece where negative infinity is one of the limits of integration. So let's look at this one first. And if we have to, we'll look at this one second. I would highly recommend doing this before you just jump in. You're going to save yourself some work if you think you've identified the one that might diverge first. So looking at that one, I'm going to write it out again. From negative infinity to 0, x e to the negative x dx. That's an equal. The limit as a approaches negative infinity of the integral from a to 0 of x e to the negative x dx. This is a one-shot integration by parts, so let's do it. U is going to equal x. dv is e to the negative x dx. du is 1 dx. V is the antiderivative of the negative x, which is e to the negative x divided by negative 1. But dividing by negative 1 is the same as multiplying by negative 1. So it's just negative e to the negative x. And so if we're integrating x e to the negative x, we're going to get uv x times negative e to the negative x minus the integral of v du minus the integral of negative e to the negative x. So that's negative x e to the negative x, so many negatives, plus the integral of e to the negative x, which is finally negative x e to the negative x minus e to the negative x. I don't need the plus c because it's just my own side work here. So that's my antiderivative. So then we're going to get the limit as a approaches negative infinity of this terrible function, negative x e to the negative x minus e to the negative x, from a to 0. So then we're going to plug in. Limit as a goes to minus infinity. If I plug in 0, I get 0 times e to the 0 minus e to the 0. Minus, if I plug in a, I get negative a e to the negative a minus e to the negative a. This right here is just going to be a minus 1. And here I'm going to do two things. Well, one thing actually. I'm going to factor out a negative e to the negative a. So I have the limit as a approaches minus infinity of negative 1 minus negative e to the a, sorry, negative a. And then I'm left with, from here, a positive a, and from here, a positive 1. So here's what I've got. I've got the limit as a approaches minus infinity of negative 1 plus e to the negative a times a plus 1. E to the negative a, well, since a is going to negative infinity, I have e to the negative infinity, which is e to the infinity, which is infinitely large. And negative infinity plus 1 is negatively infinitely large. And a really big number times a really big negative number is a really big negative number. So this is negative infinity. So the whole thing diverges. We don't even have to look at part 2, because once this piece diverges, it doesn't matter if this part diverges to infinity or negative infinity or converges to some finite value, especially if even if it doesn't, but even if this diverges to infinity, you don't get to say that negative infinity plus infinity converges to anything specifically. You have to say we're screwed, and that's what we get. That one, if they do ask what it diverges to, you can't say what it diverges to if it's specifically a negative infinity plus an infinity or an infinity minus infinity. That one's just inconclusive. It's just divergent. Cool. You have time for that fish problem. I'm sorry. So I'll get yeah. I want to do it, but I just know if I start doing it, I'm gonna run out. I'm gonna run over here. So let's look at something else. Oh, let's talk about area between curves, because a lot of people had questions about that and I didn't even get started on that. So we'll do an area between curves problem, and then I'll remember I have other fish problems that are almost the same as that. If you want to, we'll start the next class with that, or you can come see me in office hours. So let's see. You probably already saw this one. If you watched the video, I feel like I did this one already. Still worth doing though. So area between, sure, let's change it up. Y equal to x squared plus 2x and y equal to negative 3x. Okay. So I'm trying to find the area between two curves. Two things you got to do. Thing one, find where they intersect. Unless the problem says like find the area between these two curves between x equals something and x equals something, and then those are your limits of integration. But usually, more typical type of question is to say, here's your two curves, find the area between them. So the first step is to find where they intersect. Often by setting them equal to each other, but sometimes it involves like subbing one into the other one. I'm like, for example, if one of these curves was like x squared plus y squared equal to 25, then I would take y from the negative 3x and plug that in for y to then try and solve for x. So it's not always just setting them equal to each other, it's just trying to solve and take them equal to each other. Here it's setting them equal to each other. So we're going to set x squared plus 2x equal to negative 3x. We're going to typically bring everything to one side. So you get x squared plus 5x equal to 0. We're going to factor. We get x times x plus 5 equal to 0. So our solutions, our limits of integration, are going to be x equal to 0 and x equal to negative 5. And then the other thing that you can get away with not doing, but I think you should do, is you got to find which function's bigger. And the easiest way to do that without graphing them is to pick any point between these 2 points and plug it into both functions and see which function's bigger. So if I call this function f of x and this function g of x, and I plug in, say, I don't know, x equal to negative 1, f of -1 is going to be -1 squared plus 2 times -1, which is 1 minus 2, which is -1. G of -1 is going to be -3 times -1, which is +3. So on that interval, where they intersect at 0 and -5, which is the only places they cross, everywhere between 0 and -5, G is going to be the bigger function. It's bigger at one point. So we know that our area can be found by taking the integral from -5 to 0 of the top function minus the bottom function, which in this case is going to be the integral from -5 to 0 of your top function, which is -3x, minus your bottom function, which is x squared plus 2x. Now, if you happen to not check this or get it wrong and you end up with a negative answer, the fix is easy. You just go back and change the signs of everything and make it positive. Or you can even be even lazier and put absolute values around the whole thing and just say it's positive. But there can be slight issues with that if there's more than just one region, like if the graphs intersect in more than 2 points. So caution there. Finishing this off, we should simplify the integrand. -3x minus x squared minus 2x is going to be -5x minus x squared. Anti-differentiate, you get -5x squared over 2 minus x cubed over 3. From -5 to 0, you plug in 0 and you get 0 minus 0. You plug in -5 and you get -5 times -5 squared over 2 minus -5 cubed over 2. That looks like there's too many negatives. Ugh. Okay, so what do we got here? -5 times -5 squared is -125, but then the negative of that's going to be +125 over 2. And the -5 cubed is -125, but then it's a negative, so it's still -125. Here's what I would recommend if you happen to do something. This happens more often than you would think. You get some fractions where the numerators happen to be the same. You can totally get the common denominator, multiply, this by 3 over 3, this by 2 over 2. It's not that terrible, but I think it's easier to factor out the 125 and say, now you have 1/2 minus 1/3. To me, that just feels a little bit easier. That's 125 times 3/6 minus 2/6, which is 125 times 1/6, or 125 over 6. You'll get there the other way, but try to make your life simpler if you can. All right, Friday. Remind me about that problem. We'll definitely talk about it. Sorry I didn't get to it today. And we'll talk more about area between curves. And I guess we'll probably start talking about volume as well. Oh, and we should also probably talk about the survival and renewal stuff. So that's what's on my mental agenda for Friday. If you have other things, let me know.